and then later into the week, it's the template problems. And so we work our way through a series of 10 problems that focus on the 5 modalities: words, pictures, vector diagrams, graphs, and finally the algebraic description of a solution. And remember, that is what we're doing, a solution. Now, you're not going to be required to do this every time you do a problem for me in physics, but there will be aspects that you would probably want to have as you go through a problem-solving process. And again, we'll clarify that as we get closer to that. So let's just start and imagine we're doing a template problem. Now, when we start a template problem, it's a template because when you turn these in, everybody's going to look pretty much the same, which means you're going to start your template problem in your notes by you rewriting the problem. All right, so you're going to leave space. You're going to actually physically write the problem. You're going to do 1 problem per page. So you're going to copy the problem itself down, and then we'll get into the process of problem solving. Now, this is not busy work. You copying that problem down, in my mind, forces you to interact with all the information that is provided to you. So as you copy that down, handwritten, don't copy and paste. As you handwrite that out, you're going to take that information, and we're going to then move to the second part of the problem-solving process in this template, and that is to build the data table. Our data tables are always going to look alike look like this for kinematics problems. I encourage you to use velocity initial, velocity final, acceleration, delta x, and time. And so you'll build this data table, and extracting the information from the body of the problem, you'll start to pull information out. So for instance, you noticed in the reading that it said we start this problem at rest. And so you'll start with an initial velocity of 0 meters per second. They tell you that you have an acceleration of 2.8 meters per second squared. They'll tell you that you spent an amount of time. This took 7 seconds. And now whatever this object is, let's just say it's a car speeding up. They've left you with these 3 pieces of information. They're going to finally ask you in some part of the question, well, find the final velocity. So you would have to solve for the final velocity here. But you'll notice one other piece of information. One of these variables will inevitably be missing. And I'd like to come back to that in a few moments, because I think this is actually probably the most important piece of information in this data table. Oddly enough, the most important piece is the piece that they have not given you and they do not ask you about. So moving on in the template process, you would go from the data table now to creating a graph. And let's be clear, we're not actually graphing anything. We're sketching a graph. The graph I want you to sketch at this stage is a velocity time graph. And this velocity time graph should be relatively specific. It says, while it's not a graph, it should represent the situation. While it said I'm starting off with a 0 velocity, that should be reflected in the graph. If I was starting with some other velocity, that should be reflected in the graph. Maybe I was starting up here. So, but in this case, it's a 0 velocity, and we have a positive acceleration. It's speeding up. It tells us somewhere in the problem that we were speeding up, and we want to know that final velocity, and we create that sketch of this graph. What's important about this graph then, and what I want you to include in it, is the fact that the slope of that graph, we all know what that means at this point. The slope of a velocity time graph is an acceleration. And in this case, the key piece of information is that it's a positive acceleration. Based on this idea of speeding up here, the information that I've been given in my data table over here, I can surmise now that I am speeding up based on this, and that it's a positive acceleration based on everything that we know from the things that we've done up until this point. So these are the first two steps in the problem-solving process. We would continue this problem-solving process from there down. So if I was just scrolling down, you'd have time. You could see the bottom of your of that axis of that. And the next thing we would create from there would be our vector diagram. So for my vector diagram, I'm going to start off recognizing that we're covering some distance with some displacement, delta x, that we are starting with an initial velocity of 0, and that's allowed to be put in there as a number. I record it as a dot because it doesn't have any magnitude, and that we're speeding up, so therefore we're going to have some velocity final. That velocity final was brought to us by an acceleration, and since we're speeding up and my velocity is in this direction, that acceleration is again positive. So somewhat redundant, but we're looking for means and ways to figure out how we go about determining that this acceleration is positive. It's not always obvious from the problem-solving solution. We know that positive accelerations do not always speed us up. So we've got to be aware of what's actually happening with this acceleration. Is it positive? Is it negative? And like I said, eventually you won't have to do this. After these 10 problems, you get to pick and choose what parts and pieces you're going to use in your problem-solving method. But the very next thing that we're going to do then is we're going to pick our equation. And that brings us to the big four. So in the next part of problem solving, we need to hit the big four. Now, I'm going to post in the Canvas page. I'm going to post a copy of the big four, but this is what you would see when you get there. And these are the first two are the two equations you're going to derive today. A very worthwhile activity. V final. This will be the second equation that you will derive today. There'll be two more equations that we may derive later on, depending on time. Algebraically, they just fall out of the other two. And they've been algebraically solved for us for convenience. So these are our big four equations. And now we have to pick. And this has always been historically hard for students to pick an equation. How do you pick an equation from this? And actually, what I want to point out is that each of these equations have been solved algebraically for convenience. And I want to clarify what that means. Actually, what I'm interested in is what's missing from each of these equations. So if we look at all the variables we have delta x, v initial, v final, a, t, all of these variables are there. But if you notice in this first equation, it's missing delta x. The second equation is missing v final. Our third equation, we're missing time. And here in our fourth, we're missing acceleration. So this is an important image, and that's why I recreated it on in our Canvas page. But this is an important image, and I want you to see it in terms of what's missing from these equations, because if we go back, notice what was missing. What was missing was delta x. So what's missing and not asked for? Delta x, which means when I go to this now picks my equation for me. I very clearly now have a method for picking the equation, and then that allows me to go back into my formula here. V final equals V initial plus AT. That allows me to pick that equation and then move on to what? Well, now we're going to do the algebra. And let me just check what kind of formula I made up here. What was I looking for? I was looking for V final. Well, in this case, if I was looking for V final, there's really no algebra to be done. I'm going to post an example problem here before noon. And then that example problem, I'm going to show you the steps I would expect you to go through when dealing with a algebraic solution. I need everybody to get on board with this, because everybody at this point from their math background would be saying, well, I have numbers. Why don't I just plug in? Well, in this case, you can, because it's already solved for V final. The problem is that's not physics. The physics happens during the algebra stage. The physics is me manipulating those variables. And let's face it, in practice on the AP exam, there's going to be problems where there are no numbers at all. So you have to get good at algebraic manipulation. So I think this is a good place to stop for today. I would like you to work your way through the problems, through the tutorial, to discover those first two equations. Again, incredibly instructive as to how those two equations came about from our graphical method. Second, I'd like you to dive in and start in on the template problems. So you'll be following that template method and getting up to the point where you've at the very least created your graph and more than likely your vector diagram, and you've chosen your equation. You can play with the algebra, but you might want to just make sure you're checking my example to see that you're sort of falling in line and doing the right thing there. Okay, gang. Tomorrow for me, I'm going to be answering questions. So we'll have the chance to answer some questions on those things. And let's just be clear, the template problems will be due in a week, this coming Monday. So they'll be due then. All right, that's very quick. Does anybody have any questions for me? All right, if you don't have questions for me, Mr. Godak, you can take over from here.
Okay. All right, just wanted to show you a couple things here. Just while I've got it here. Here's just to reiterate what Mr. Withers just said. So building equations, this activity is the thing he said is a good activity for you to help develop the first two big four equations. If you click on the image itself, it brings up the activity as a PDF, which you should open up. These big four equations you're going to use through all of physics, and we're going to be using them in calculus. So this is the development of them, and here's the equations that he just mentioned. And then the instructions for the template problems he has below. The template problems are in a PDF, and he's going to have an example coming up here soon. So make sure you check the physics page. In terms of for me, there's a couple things I need you to be finishing up. One is to finish your limit lab and to submit photos of that lab. So I'm specific about starting at page 257 through the end of the lab is what I'd like to see. I'm interested in this description of why is it legal to consider the limit of a function at a whole. And I am looking for really very good, precise representations for each of these examples. Remember I said things are going to get weird in these examples. Lots of types of discontinuities are going to pop up in these. And that's what I'm looking for you to deal with. is if the left and the right-hand limits do not agree, if they are not equal, then the function does not have a limit at that value. But the function may actually have a value. So, and that's what the two final questions are looking for. I don't want one sentence answers. I don't want just phrases. I want you to use words, sentences, examples. You're proving to me whether or not these statements are true or not. So that's the first thing, is finishing that. I would highly, again, encourage you to talk to other people before you hand these in. Also have, last week, I think it was either Wednesday or Thursday, I put up a picture of an example of what the last section should look like. This is problem number 1, having a graph, a table with increments of 1/100th, 3 to the left and 3 to the right of the limiting value, left-hand limit with proper notation, right-hand limit with proper notation, and the overall limit. And finally, the value of the function at that point. So, and we're going to be interested in when the limit and the value are the same, or if they're different, and what that means. So that's the first thing, is finishing up that lab. Second, and I think the due date here is in the next couple days, or probably by the end of the week. But you're going to want to get it done sooner than later, else things will pile up. 8 Khan Academies are in there, ready to go. I saw a couple of people working on this morning, and they're really pretty quick because they're from graphs and tables. You're not going to be doing a lot of calculations. So let's knock out those cons as well. Because then what I'm asking you to do today is to take a look. This is the first time that we're going to be taking notes. You're going to go to the link 2.1, limits and rate of change. It's going to take you to this page where it has 2 videos that I've made, one for day 1, which is today, and the other for day 2, which is tomorrow. You are going to be watching this video and then practicing some problems out of the textbook. I've got a link to the textbook. When you click on it, it'll bring up the textbook PDF. I would suggest maybe downloading it to your Google Drive so it's always there. And this is our textbook for the course. You can tell it didn't like, it doesn't pull up, then just hit download, and then the PDF will be there. And you're going to be practicing a couple problems, and if you look on the page, all the answers are there. All the answers to the odds and the even problems are there. So copying down answers isn't going to do you any good. So the first 4 problems involve some kind of calculations. You're going to want to make sure that you are making sure you understand why you're getting those answers. There's some graph questions as well that are going to go on in there. So finishing up the lab, doing some con, but I would say one of the important things to do today, because I'm moving on tomorrow, the con and the lab aren't due until the end of the week. Watch that video, practice some problems, because then come tomorrow, you're going to watch the second video, and our goal tomorrow is to determine the limit from the equation of the function itself. So we're not going to want to be working from the graphs anymore. You can see tomorrow I'm going to be assigning some problems between like 7 and 28 when you're given the equation and you're trying to evaluate it just from the equation. So don't get behind today. Make sure you watch that video today before tomorrow. Quick little review of what you're going to see today in the video. So in the video today, I'm going to be talking about instantaneous speed and versus average speed. Your average speed as you're driving down the road compared to your instantaneous speed. We'll have a discussion about that in the video. I'm going to give you 2 equations. Now, they are technically big 4 equations that Mr. Withers is giving you. They don't look like it now, but we'll talk about it later. I'll come back and we'll work with them later. But you just need to use these equations, and they are given to you in the video. Simple calculations to find average speed and instantaneous speed. The rest of the video is just doing a little review from limits from graph, which we've done before. So the video is really, the only thing new is this speed idea, but the graph things we've done before and the couple problems I'm asking you to do in the book shouldn't take very long either as well. Again, everything's kind of thinking about and hinging on looking for types of discontinuities. We've talked about, I don't even know if that's spelled right or not, but there's 3 types of discontinuities that we've discussed in class, and those of you who haven't been in class, There is, can we really quick in the chat, can somebody name me one type of discontinuity we would see in the graph? What kind of discontinuity would I see in the graph itself? A jump, okay, that's the first one. A jump discontinuity, and that usually comes from piecewise functions. And a jump discontinuity would look maybe something like this. And this would be a case where the left and the right-hand limits would be different. Coming in from the left of where this jump is and coming in from the right of where this jump is, the left and the right-hand limits would be different, so therefore there would be no limit. Okay. How about another type of a discontinuity? A hole. Excellent, Olivia, thank you, and Danny before. A hole in the graph, we talked about that with rational functions. That is a point discontinuity. And it's also sometimes, I don't know if Mrs. Miller described it this way or your Algebra 2 teacher, it's a removable discontinuity. You can actually remove holes from equations really easily because if you remember, it's the same factor in the numerator and in the denominator. Cancel them out, you fill in the hole. So, but if it did have a hole in it, the left and the right-hand limits are the same. So there might be a limit at that hole. In fact, there is going to be a limit at that hole, and that's one of the questions that you're going to be answering in the lab. The last type of discontinuity. Clay, endpoint is interesting that you mentioned that because we'll talk about endpoints, meaning that if I have the function comes to an end and there's nothing over here to the right of it, that actually will have, it's not a discontinuity because apparently, because the function doesn't have a domain afterwards. So we're not gonna, well, endpoints are a weird thing and we'll talk about them soon. But we got jumps, holes, here you go, you guys are missing the big one. What's the last one where we have a break in the graph? There we go, Olivia, thank you. Asymptotes. And an asymptote is an infinite discontinuity. And obviously, we know what asymptotes look like, but just keep in mind, we're thinking about limits. So even though the function's not defined at the asymptote, does it have a limit? How about a big thumbs up or thumbs down? How many people think at this asymptote there would be a limit? Thumbs up, yes. Thumbs down, no. At this asymptote, would there be a limit? I'm seeing thumbs up. Excellent, yes. And that limit would be positive infinity because it approaches from the left and from the right to positive infinity. Is it possible to have an asymptote that doesn't have a limit? Well, sure. It's that normal old behavior when one side goes to positive infinity and the other side goes to negative infinity. That would not have a limit. So we want to be thinking about these types of discontinuities as you're doing the end of that lab. That's what you're going to wind up seeing is a lot of those types of discontinuities. But you're also then going to wind up seeing that in some of the example problems as well. In what we're going to be looking at over the next couple days in terms of evaluating limits from equations and not necessarily from the graphs. So tables first, graphs second, and now we're going to then tomorrow be moving on to equations. Questions about what you guys are going to be working on? I know some of you have already started working this morning, and I can see some of the work in Khan, and some people have even started uploading their lab. Make sure also, I don't know who's in this group, but make sure you're checking Canvas in your gradebook in Canvas, because some people still have not handed in the smooth curve lab. It's sitting as a big 0. And if that's the case, let me know if there was a tech issue or whatnot, and we'll work it out. All right, I think that's it for me, Mr. Withers. Anything from you?
I think I'm good.
All right, guys. Now tomorrow we're gonna again be here at 8 and 10. We're gonna do the same thing for both. So you can choose to come to one or the other, or you can come to both. It wouldn't hurt you to listen in on if some questions pop up, especially tomorrow, because tomorrow we're expecting some questions. All right. If that's nothing from you guys, we'll stick around for a second if somebody wants to ask an individual question, but we will hear from you and see you tomorrow. Have a good day, everybody. Sun just came out. Bye.